Okay, I think we'll get started. So today we're going to go beyond our Lewis structures that we've been talking about and bring them to life by seeing how they can go into 3 dimensions. So today will serve as the simple, very basic physical concept as to why molecules take their geometric shape. And this is called Vsepr, or VSEPR, stands for valence, shell, electron, pair, repulsion. And the core idea here is that sources of electron density are going to want to try to get it as far apart as possible. So if you remember way back a couple lectures ago where we were talking about charges, and we looked at charges confined to a sphere and what shapes they would make if they were allowed to get as far apart as they can from each other. That's the same idea here, and you'll recognize some of these geometric shapes as we go along. Now, what is the source of electron density? It's either a bond or a lone pair, as indicated in the Lewis dot structure. So you can read directly from the Lewis dot structure for any given atom what the sources of electron density are. Now, one important thing, though, whether it's a single, double, or triple bond, that still counts as a single source of electron density, because a double bond is kind of, those electrons are together, all 4 of them. So we don't treat that as 2 separate sources of electron density, just one source. Okay, well, let's see how we do this. The first thing we do is develop what's called the electronic geometry. And in this case, we look for simply the source of electron density, bonds or lone pairs. And again, whether it's a double, single, triple, doesn't matter. That counts as one source of electron density. And they fall then into categories depending on how many there are, and they take on the geometric shapes that we saw earlier. So if we have 2, then to get as far apart as possible, we have to be linear. 3 will remain in the plane and be trigonal planar. 4 is the first time we come up out of the plane and are tetrahedral. And then 5 is where we create a trigonal bipyramidal shape, and 6 octahedral. So let's take a look at some of these shapes. Now, we'll go through the first ones pretty quickly, but we'll try to see this in 3 dimensions here now. So these tan lobes, think of that as a source of electron density. A bond, again, a bond or a lone pair. And then where I'm holding here is the central atom about which those extend. So here, 2 sources of electron density as far apart as possible in 3D space. They form a line. 3 sources of electron density are trigonal planar. All sources lie in a plane, and they are getting as far apart as possible by having 120 degrees angle between them. Now, if we were stuck to a plane, then the next shape would be a square, but we can pop up out of the plane and use the full 3-dimensional space, and that's a tetrahedral. We really want to get a good sense of tetrahedral geometry. A couple of ways to look at it. You can look at it this way and see 1 lobe sticking up and then 3 down in kind of a pyramid shape. Another way to look at this is to look at 2 V shapes, one coming side to side like this, and then one coming at you and away from you. That's a tetrahedral electronic geometry. Here's 5 sources. This is the only shape that has distinct angles, so 2 distinct angles. Here, there's a 90-degree angle, and then with these 3, they are in a trigonal planar shape, so 120 degrees. And then another 90 degrees here. So that's a trigonal bipyramidal shape. The bipyramid comes from, if you imagine this top part forming a triangle-shaped triangle base pyramid, and then the bottom part also forming a triangle base pyramid. So that's trigonal bipyramidal. And then finally, 6 sources of electron density. Octahedral shape, and here everything is 90 degrees. A group of 4 form a plane, and then one comes out at you and one away from you. All right, so those are the electronic geometries. Now, to get the actual molecular geometry, then we have to look at what are lone pairs and what are bonds. And again, double, single, triple count as one. So to get the molecular geometry, we find the electronic geometry first. And then the subgeometry to that is the molecular geometry. Now, with the case of linear, then if we have a central atom and two others, then that'll be a line. Also, if we simply have two atoms, of course, that'll be a line. 2 points determine a line. But here we've got, sorry, I should have had it this way. So a lone pair here, and then a bonding pair here. But generally, we're thinking about something like this, where we have two peripheral atoms coming off of the center. And again, we have a linear geometry. So the molecular geometry is also called linear. So this is linear, linear. Linear electronic, linear molecular. Okay, now let's look at trigonoplanar. If all of the sources of electron density are bonding pairs, then we call this trigonoplanar. So it would be trigonoplanar, trigonoplanar. So trigonoplanar, trigonoplanar. But if one happens to be a lone pair, then we have trigonoplanar electronic geometry, bonding pair, lone pair. But the molecular shape, we don't think about the lone pair's lobe. So here we have just a V shape or a bent shape. So that's trigonoplanar, trigonoplanar, bent is the geometry. All right, let's go to the tetrahedrals. So again, when they're all bonds, then the geometry name is the same as the electronic name. So here's an example where all of these are bonded to some other atom. So we have tetrahedral, tetrahedral. When one of those bonds is replaced with a lone pair, so this lone pair here, then this stands like a pyramid. And so we're tetrahedral, trigonal, pyramidal. Trigonal, pyramidal. Looks like that. And then finally here, if we have two lone pairs, then we're bent. Now notice this is a different bent than this. Both these have a subgeometry of bent, but this is a tetrahedral electronic geometry. This has a trigonoplanar electronic geometry. All right, let's move to the trigonal bipyramidal. So again, if it's all bonds, then it is trigonal bipyramidal. So trigonal bipyramidal, trigonal bipyramidal. Now, we have a bit of a choice here, and this brings up an important topic, that the lone pair, because there's not a counter nucleus here, a positive charge, sucking in some of that electron density, it takes up more space than the corresponding bonding electrons. And so the lone pair is going to, the molecular geometry is going to want to adopt a geometry such that the lone pair has the most space. And so for trigonal bipyramidal, since there's an asymmetry to these positions, this so-called axial and equatorial positions, axial, equatorial, the lone pair comes in the equatorial position right here. So as one of the trigonoplanar spots. And so the result of this is something that's called a seesaw. So it acts kind of like a teeter-totter or a seesaw for kids. And that's the name of the geometry. Okay, so again, axial, equatorial. We fill, or we put the lone pair on the equatorial position, not on an axial position. And then that extends for 2, right? They still want to get as far apart as possible. Now even more so do we want to put the lone pairs on the axial position. And we end up with what's called T-shape. So a T-shape geometry. So trigonal bipyramidal, T-shaped. And now let's put all 3. Well, they're going to certainly be in the trigonoplanar position here, so all equatorial. And then the axial sources of electron density are the bonds, and so that's linear. So we get another linear subgeometry, but it's under the tetrahedral electronic geometry. So tetrahedral, linear. All right, let's go to the octahedral. So again, all spots filled, so with a bond, not a lone pair. So this is called an octahedral geometry. So octahedral, octahedral. We lose 1, doesn't matter where because of the symmetry. And so we choose any one of those. That's where the lone pair goes. But then, the molecular geometry, again, we don't think of the lone pair when we think of the subgeometry, the molecular geometry. This has got a square plane, right? And then 1 sticks up, so that'll be square pyramidal. So this is octahedral square pyramidal. Now this has induced an asymmetry, right? So the lone pair's down here. We have a choice to put our second lone pair. Do we put it here or do we put it here? And again, following the principle that the lone pairs are bigger, so they want to be further apart. We will put these opposite each other. And so the lone pairs are opposite to each other. We don't call this axial equatorial because these are equal spots. But since one was there, the other goes opposite. And then we're planar. So all the bonds line to plane. And so we call that octahedral square planar. That's about as far as we go. If another one would come in, it would be called T-shaped, but we really don't see that very often. All right, so that's a walk through the molecular geometries. So again, we first find the electronic geometry, that's the base geometry, and then we find the subgeometry to give us the overall shape of that molecule. Key principles for the electronic geometry, we count lone pairs and bonds equally, and bonds, whether double, single, or triple, count as 1. Because again, a triple bond has, it's really talking about all those electrons acting as one kind of unit, that triple bond. All right, let's take this and see if we can just extend this idea of the lone pair being larger and figuring out the geometry based on that and where to put the lone pairs to an example, a similar example. Now we'll go SF6, right? So that would be octahedral. So this is octahedral, octahedral. This is SF5I, still octahedral, octahedral. Okay, so this is still an octahedral, electronic octahedral molecular. But one of the bonds, now let's imagine this. Imagine this was, these are the fluorines, and imagine this was the iodine right here. Okay, now where does the next iodine go? Well, iodine is bigger, so with SF4I2, the iodines will be on opposite sides. So let's see here. Imagine now that these were replaced, these two, the top and the bottom, were replaced now with iodines. They're bigger, so they're going to want to be opposite each other. So we still call this octahedral, octahedral, right? Still octahedral because there's no lone pairs. But using those ideas of where to put the larger lone pairs, then we can get the right structure when we have the situation like this. This doesn't matter, right? That would be the same no matter what. But here, where do we put that second iodine? All right, and the last thing I want to talk about today is now that we have a structure in 3D space, we can talk about an overall net dipole. And we had talked about, with Lewis structures and electronegativity, we talked about polar bonds. And if we consider just any two pair that are bonded, we can talk about a dipole between, consisting of the partial positive and partial negative charges. But collectively, those polar bonds add vectorially to determine an overall molecular dipole. So let's look at a couple of examples here. So water, polar bonds in this direction. There's a net dipole straight up. And why straight up? Because we have a polar bond this way and a polar bond this way. And so adding vectorially, we're straight up. Okay. Here's a similar example here now. Partial negative here. Then the carbon is partial negative compared to the hydrogens. So now we have a kind of a vector this way, a small vector this way, right, and a longer vector this way. And the net result of all this is a vector straight up the molecule. So the dipole moment is in that direction. Now let's look at the same molecule, but change the hydrogens to fluorines. Now we have a pretty strong dipole in this direction, or polar bond in this direction, but even stronger in this direction, because fluorine, the most electronegative, more electronegative than oxygen. So we have a net dipole downward, right? And so the vector sum here would be, right, there's our vector sum pointing downward. And finally, let's look at, well, not finally, I'll do some 3D stuff here too, but finally on the board here, let's look at these very strong polarity in these bonds. But by symmetry, they all cancel. So the vector sum here and we can see that with the symmetry of the molecule. And we'll come back to this idea after we really talk about symmetry carefully in the next couple of days. And we'll be able to make some good connections and say some things about the net molecular dipole. Let me just quickly go to 3D here. Let's look at ammonia here. So imagine this is a nitrogen, and these are the hydrogens. Now don't worry about the lone pair here. We just look at any pair and say, oh, nitrogen more electronegative than the hydrogen, so there'll be a net dipole in this, a net polar bond in this direction, and then likewise this way and this way. So we'll have sort of three pointing up these bonds, and so that will give us a net dipole pointing straight up. And or when I point it at you, it'll be pointing straight at you here, coming from the net 3D vector sum of the individual polar bonds. All right, so now what you really want to do is practice your geometry assignments. It's really important to get this down because this is the basis for how chemical reactivity happens. Reactions take place in 3D. Chemistry is a 3D event. And so we have to really develop our 3D thinking here and be able to see molecules as 3D objects. And the next couple of days, when we talk about valence bond theory and then talk about symmetry and what are called point groups, we'll be able to really solidify some of these ideas. And very quickly, you'll become very good at seeing chemistry in 3 dimensions.